Welcome to our exploration of the magnetic effects of electric current. In this chapter, we'll uncover how electricity and magnetism are deeply connected, shaping much of the technology we use every day. From the invisible lines of magnetic fields to the powerful machines that run our world, understanding these concepts is key to grasping modern science. Let's embark on a journey through the fascinating world where electric currents create magnetic fields and discover how this knowledge powers motors, generators, and so much more. Magnetic field is an invisible region around a magnet or a current-carrying conductor where magnetic forces can be detected. It's represented by lines that show the direction and strength of the force. These lines emerge from the North Pole and enter the South Pole of a magnet, forming closed loops. The closer the lines, the stronger the field. Magnetic fields are crucial in understanding how electric currents interact with their surroundings, influencing everything from compass needles to electric motors. Right-hand thumb rule is a simple way to determine the direction of the magnetic field around a current-carrying wire. Imagine holding the wire in your right hand, with your thumb pointing in the direction of the current. Your curled fingers then show the direction of the magnetic field lines circling the wire. This rule helps us visualize the invisible magnetic effects created by electric currents, making it easier to predict how devices like motors and solenoids will behave. Electromagnetic induction is the process by which a changing magnetic field creates an electric current in a conductor. This phenomenon was discovered by Michael Faraday and is the foundation of many electrical devices. When a magnet moves near a coil of wire, or the coil moves near a magnet, an electric current is induced in the wire. This principle is used in generators to produce electricity and in transformers to transfer energy between circuits. Solenoid is a coil of wire, usually wound in the shape of a cylinder. When electric current passes through it, the solenoid creates a strong, uniform magnetic field inside. This makes solenoids useful for creating controlled magnetic fields in devices like electromagnets, relays, and even MRI machines. The strength of the field depends on the number of turns in the coil and the amount of current flowing through it. Electric motors convert electrical energy into mechanical motion using the interaction between magnetic fields and current-carrying conductors. Inside a motor, a coil of wire rotates within a magnetic field. When current flows through the coil, it experiences a force that causes it to spin. This spinning motion is harnessed to do useful work, from turning the blades of a fan to powering electric vehicles. The design of motors relies on the principles of electromagnetism. Electric generators work on the principle of electromagnetic induction. When a coil rotates in a magnetic field, it cuts through the magnetic lines of force, inducing an electric current in the coil. This process converts mechanical energy, such as spinning a turbine, into electrical energy. Generators are essential for producing electricity in power plants, making them a cornerstone of modern civilization. Magnetic flux measures the total magnetic field passing through a given area. It's a key concept for understanding how magnetic fields interact with objects. The amount of flux depends on the strength of the magnetic field and the area it passes through. Changes in magnetic flux are what induce currents in coils, as seen in generators and transformers. This concept helps engineers design efficient electrical devices. Transformer is a device that changes the voltage of alternating current AC electricity. It works by using two coils of wire, called the primary and secondary coils, wound around a magnetic core. When AC flows through the primary coil, it creates a changing magnetic field which induces a current in the secondary coil. There are step transformers which increase voltage and step-down transformers which decrease it. Transformers are vital for efficient power transmission. Alternating current AC and direct current DC are two types of electric current. AC changes direction periodically, while DC flows in one direction only. Most household electricity is AC because it's easier to transmit over long distances. DC is commonly used in batteries and electronic devices. Understanding the difference between AC and DC is crucial for working with electrical systems and choosing the right devices for specific applications. Galvanometer is a sensitive instrument used to detect and measure small electric currents. It works by using a coil suspended in a magnetic field. When current passes through the coil, it experiences a force that causes it to rotate, moving a pointer on a scale. Galvanometers are essential tools in laboratories and for testing electrical circuits, helping engineers and scientists observe the flow of electricity with precision. In an electric motor, the commutator is a crucial component that ensures the current direction in the coil reverses at the right moment. This reversal keeps the motor spinning in one direction. The commutator works with brushes to maintain electrical contact as the coil rotates. Without the commutator, the motor would stop or change direction erratically, making it essential for smooth operation. When an electric current flows through a conductor placed in a magnetic field, it experiences a force. This force is what makes electric motors work. The direction of the force depends on the direction of the current and the magnetic field. This interaction is a fundamental principle in electromagnetism and is used in many devices from loudspeakers to maglev trains. Lemming's left-hand rule is a handy way to predict the direction of force on a current-carrying conductor in a magnetic field. If you stretch your left hand with the thumb, forefinger, and middle finger at right angles, the forefinger points in the direction of the magnetic field, the middle finger in the direction of current, and the thumb shows the direction of force. This rule is essential for understanding how motors and other electromagnetic devices operate. Loudspeakers transform electrical signals into sound using the principles of electromagnetism. Inside a loudspeaker, a coil attached to a diaphragm sits within a magnetic field. When an audio signal passes through the coil, it creates a changing magnetic field that moves the diaphragm back and forth, producing sound waves. This process allows us to hear music, voices, and other audio from electronic devices. Magnetic compass is a simple device that uses a small, freely rotating magnetized needle to indicate direction. The needle aligns itself with Earth's magnetic field, pointing toward the magnetic north. Compasses have been used for centuries in navigation, helping travelers and explorers find their way. The principle behind the compass is the interaction between the needle and the planet's magnetic field. D-currents are loops of electric current that are induced within conductors by changing magnetic field. These currents flow in closed loops and can cause energy loss in the form of heat. While often undesirable, eddy currents are used in applications like induction heating and electromagnetic braking. Engineers design devices to minimize unwanted eddy currents or harness them for useful purposes. Electromagnets are magnets created by passing electric current through a coil of wire. Unlike permanent magnets, electromagnets can be turned on and off by controlling the current. They are widely used in devices like electric bells, relays, cranes for lifting heavy metal objects, and MRI machines. The strength of an electromagnet can be adjusted by changing the current or the number of coils. A relay is an electrically operated switch that uses an electromagnet to open or close a circuit. When current flows through the coil, it creates a magnetic field that moves a lever, switching the circuit on or off. Relays are used to control high-power devices with low-power signals, making them essential in automation, vehicles, and home appliances. Magnetic levitation, or maglev, trains float above the tracks using powerful electromagnets. By creating magnetic fields that repel and attract, these trains eliminate friction, allowing for incredibly smooth and fast travel. The principle relies on electromagnetic forces to lift and propel the train, making maglev technology a marvel of modern transportation. Magnetic hysteresis describes how a magnetic material retains some magnetization even after the external magnetic field is removed. This lag in response is important in designing transformers and electric motors, as it affects energy efficiency. Materials with low hysteresis are preferred for devices that need to switch magnetic states frequently, reducing energy loss. Magnetism isn't just a scientific concept, it's part of our everyday lives. From the speakers in our phones to the motors in our appliances, magnetic effects of electric current are everywhere. Even credit cards use magnetic strips to store information. Understanding these principles helps us appreciate the invisible forces that power our modern world. Working with electricity and magnetism requires careful safety measures. Strong magnetic fields can affect electronic devices and even medical implants. It's important to follow guidelines when handling electrical equipment, especially in labs or industrial settings. Proper insulation, grounding, and awareness of magnetic fields help prevent accidents and ensure safe operation. Magnetic effects play a vital role in communication technology. Microphones and speakers use electromagnetic principles to convert sound into electrical signals and back. Hard drives store data using magnetic fields. Even wireless charging relies on electromagnetic induction. These applications show how magnetism is at the heart of modern communication. Medical technology benefits greatly from magnetic effects. MRI machines use powerful electromagnets to create detailed images of the body. Electromagnetic fields are also used in therapies and diagnostic tools. Understanding how magnetism interacts with biological tissues helps doctors diagnose and treat illnesses more effectively. Industries rely on magnetic effects for automation, manufacturing, and quality control. Electromagnets are used in cranes to lift heavy metal objects, while sensors detect metal impurities in products. Magnetic separators help purify materials, and electric motors drive conveyor belts and machinery. Magnetism boosts efficiency and safety in industrial processes. Transportation systems use magnetic effects in many ways. Electric trains and subways rely on motors powered by electromagnetic forces. Maglev trains use magnetic levitation for high-speed travel. Even traffic lights and sensors use electromagnetic induction to detect vehicles and manage traffic flow efficiently. Scientists use magnetic fields in research to study materials and fundamental physics. Particle accelerators use powerful magnets to steer and focus beams of particles. Magnetic resonance is used to analyze chemical structures. These advanced tools help expand our understanding of the universe and develop new technologies. Educational tools use magnetic effects to teach students about science and technology. Demonstration kits show how electromagnets, motors, and generators work. Interactive experiments help learners visualize magnetic fields and understand their applications. These hands-on experiences make learning about magnetism engaging and memorable. We've journeyed through the magnetic effects of electric current, exploring everything from basic concepts to real-world applications. Understanding how electricity and magnetism interact unlocks the secrets behind many modern technologies. Whether it's powering a train, diagnosing an illness, or simply listening to music, the principles of magnetism are all around us. Keep exploring, and you'll find even more ways these invisible forces shape our lives.